All right. So in Chapter 15, Section 4, we're going to look at solving exponential and logarithmic equations. And really, I'm just going to go through and do a bunch of different examples to kind of give you a feel for how this is done. That also includes some like real world kind of problems. So we'll use some deal with some story problems and some special cases where we have specific models created in order to do stuff like this. But let's start with just some basic like algebraic examples. So let's say we have 14 times 1/3 to the x is equal to 126. So the first thing, oops, I meant x minus 1. So the first thing we'd want to do is we want to get the part with the exponential part by itself on one side of the equation. We notice the x is in just one location. So the first thing we have to do is get rid of this 14 that's being multiplied to the exponential piece. So to do that, we'll divide both sides by 14. So that's going to leave us with 1/3 to the x minus 1 is equal to 9. And now there's a couple of different ways you could approach this here. So one way you could do this, you could rewrite 1/3 and 9 so that they have the same exponential base, which is fine. What I prefer to do is I'm just going to use a logarithm to deal with the situation. It's a little bit more powerful than you need in this situation, but it works, and I think it makes life a little bit more simple. So what I need to do is I need to cancel out the base of this exponential of 1/3. The tool to cancel the base of an exponential is a logarithm with the same base. So what I'm going to do is I'm going to take the log base 1/3 to both sides of this equation. So we know that log base 1/3 cancels exponent base 1/3, leaving us with just the exponent. And now we can calculate log base 1/3 of 9. And this is one you could do by hand, but we've also talked about how to do this on our calculator. So let's just use our calculator to do this. So do log base 1/3 of 9, which gives us -2. So when I add 1 to both sides, I get x is equal to 1. And we're done. Let's do another. So let's call this example A here. So example B, say we have 12 times 3/2 to the x over 5 equals 27. So again, the first thing I'm going to want to do is to get that exponential part by itself. So let's divide both sides by 12. So that's going to leave us with 3/2 x to the x over 5. And if I divide 27 by 12 and reduce that fraction, I get 9/4. And again, we could do some tricky things and try to rewrite these so that they have the same exponential base. But I'm just going to use a logarithm here. So I need to cancel out this exponent base of 3/2. To cancel an exponent base, I need to use a logarithm with the same base. So the logarithm I'm going to do to both sides is going to be log base 3 over 2. And so we know that log base 3 over 2 cancels exponent base 3 over 2, which just leaves us with x over 5. And then log base 3 over 2 of 9 over 4, we can just do on our calculator. So again, I'm going to press the math button, select the log base command, do 3 over 2. This is also something you could do by hand, but we don't really need to. When we do that, we get 2. And now we just need to solve for x, multiply both sides by 5 to get 10. And so there's that. Let's look at another one that's maybe a little bit more complicated. So I have 3 to the x plus 3 to the negative x over 4, which is equal to 12. So here I notice that I have exponentials in more than one location. So this is going to become a little bit more complicated. So the first step, however, is going to be to get rid of this dividing by 4. To do that, I'm just going to multiply both sides of this equation by 4. So here the 4's will cancel out, leaving me with 3 to the x plus 3 to the negative x is equal to 48. Now remember that 3 to the negative x, that a negative exponent just really means a reciprocal. So we have something like this. Now this looks a little bit like a rational function that we just got done dealing with, right? Because I have a variable in the denominator of my fraction. So what I'm going to do is just like I would do with rational functions, is I'm going to kind of clear the fraction here. And clearing the fraction is going to be very easy in this case because I only have one denominator that has a variable in it, that's 3 to the x, and really that's the only denominator other than 1. So I'm just going to multiply both sides of this equation by 3 to the x. So that's going to give me 3 to the x times 3 to the x plus 3 to the x times 1 over 3 to the x equals 3 to the x times 48. Now if I multiply these together, I can multiply 3 to the x and 3 to the x together. Remember that when we multiply exponentials, let's see, we do like x to the a times x to the b is equal to x to the a plus b. So here we're going to have 3 to the x plus x, or really just 3 to the 2x. 3 to the x times 1 over 3 to the x is just 1, right? Those guys cancel. And then 3 to the x times 48. Those are not like terms because the exponents aren't the same or the bases aren't the same, so there's no way to multiply these together. So I'm just going to write it this way. So I'm going to move everything now onto one side, and notice that this looks, you know what? Okay. Notice that this looks a little bit like a quadratic. And you'll notice that maybe the way I wrote it isn't so obvious to see it's a quadratic. So let's go back and maybe make that a little bit more obvious for you guys. So let's go back to this part where we had 3 to the x times 3 to the x. Isn't that going to be the same as 3 to the x squared? So let's rewrite this as 3 to the x squared. Now, they mean the same thing. It's just that now we look much more like a quadratic, right? And you might say, I still don't see it. Well, let's do this. Let's make a substitution to make it a little bit easier for you to see. Let's replace the 3 to the x's with y's. Okay. Well, this definitely looks quadratic to me. So to solve this quadratic, I could try either factoring, or if I can't factor, I can use the quadratic formula. Really, I can always use the quadratic formula. I just prefer to factor usually because it's quicker. Here it should be pretty obvious. There's not two numbers that multiply to 1 and add to give us negative 48. So if we apply the quadratic formula, I'm going to get y equals negative b, which is going to be negative of a negative 48, or just positive 48, plus or minus the square root of negative 48 squared times 4 times 1 times 1 all over 2 times 1. So 48 squared minus 4 is 2300. And we can probably do a bit better than 2300. So that looks like it's divisible by 4. Sure is. 375 is divisible by 5. Actually, it's divisible by 5 twice, so 25. So what this really simplifies down to here is I can say this is the square root of 4 times the square root of 25 times the square root of 23, oops, or 2 times 5 times the square root of 23. And I notice here that each of these coefficients is divisible by 2. So let's go ahead and do that. So 24 plus or minus 5 square root of 23. But remember, in this problem we weren't asked to solve for y, we're solving for x. So let's go back and remember y is equal to 3 to the x. So I'm just going to replace my y with 3 to the x. Okay. So now this is going to break into two equations. So 3 to the x is equal to 24 plus 5 root 23, and 3 to the x is equal to 24 minus 5 square root 23. Now, one thing I have to be careful about is that I know that I can't take the logarithm of a negative number, which is what I'm going to have to do. So I want to see if 24 minus 5 times the square root of 23 is a negative number or not. I'm not really sure what that's going to be just by looking at it, but if I type that into my calculator, I do see that it is positive, so it is okay. If this were in fact a negative value, you could just get rid of that one right away, because you can't take the logarithm of a negative number. However, neither of these are going to be negative, so what we'll do is we'll try to cancel this exponent base of 3. To do that, we're going to use the logarithm of the same base. I'm going to do that to both sides for both of these problems. So we know that those cancel. And then log base 3 of that is just going to be something I can type into my calculator. So again, I'll go to the math button, choose the log base command, type my 3 in, and then I'll do 24 plus 5 square root 23. Press enter, and I get 3523. So 3 decimal places I think will be sufficient for us. If I do the same thing here, those cancel. And rather than retyping this all in, I can press second and enter, which will give me the last line I typed in. And I can just scroll over here to the plus and turn it into a subtraction symbol. And that gives me negative 3523. So remember, logarithms can give you a negative answer. That's okay. What's not okay is I can't take the logarithm of a negative number. So that's what I was worried about earlier, is that whether 24 minus 5 square root 23 was positive or negative. Since it's positive, we don't have any problem. We can get a negative result from a logarithm. That's okay. We can't take the logarithm of a negative number. That's what we have to be a little bit careful about. So that's about as tricky as the exponential solving problems are going to get. Let's look at some problems that involve logarithms now. And now I know we used logarithms in most problems, but the beginning part of the problem didn't have a logarithm in it. So the first thing I'd want to do is I want to get the part with the logarithm by itself. So I got to get rid of this 3. So we'll just divide both sides by 3. So those are going to cancel out. So I'm going to have log of x squared is equal to 2. And now what I need to do is cancel out that logarithm. So remember that logarithms and exponent bases are inverses of each other. So in the previous problems, I used a logarithm to cancel an exponent base. In this problem, I'm going to use an exponent base to cancel a logarithm. So I'm going to look at this logarithm. I notice that there is no base written here, but that's okay. Remember, we defined the common logarithm as log base 10, and we abbreviate it as log with no base written here. So I know that when there's no base written, it's just base 10. So what I'm going to do is I'm going to do the exponent base of 10 to both sides. And now I'm writing the 10s comically large because I don't want you to confuse this 10 with a multiplying by 10. This is an exponent base of 10. That's a very important distinction. So those are going to cancel, leaving me with x squared is equal to 100. And I can then just square root both sides to get x equals plus or minus 10. But I now need to be very careful here because I know that logarithms have I can only take the logarithm of positive values, right? So I have to be very careful about this. So I need to make sure I'm checking my answers for these logarithmic equations because I can get extraneous solutions here. So I need to make sure that when I plug 10 or negative 10 back into the original problem, the parts inside the logarithm have to be positive. They can't be 0, they can't be negative. So if I go all the way back to the very beginning, if I plug anything in for x squared, it's going to be non-negative, right? Because I'm squaring it. And because what I'm plugging in is non-zero, I know the result has to be positive. So both of these are going to be okay, right? 10 squared is 100, and negative 10 squared is also 100. So we're okay here. Let's do one that's a little bit trickier. So let's say we want to do the natural log of 3x minus 2 plus the natural log of x minus 1 equals 2 times the natural log of x. So what I'm going to do here is I'm going to combine things. I need to get single logarithms on one or both sides. If I look at the right side, I already have a single logarithm here. If I look at the left side, though, I have 2 separate logarithms. What I want to do here is I want to combine these into a single logarithm. So I can do that because they're added together by using the product property of logarithms. Remember, we said that log of AB is the log of A plus the log of B. Right? Remember that was the product property? So I'm going to use that in reverse to condense these into the single logarithm. And I guess as long as I'm at it, I'm going to use the product property, the power property over here to get rid of this coefficient of 2. Because that's going to also make my life a little bit easier. Remember the product property said the log of x to the c is c times log of x. So I can use the product property here, or the power property, jeepers creepers, to rewrite that as the natural log of x squared. Okay, so now that I have a single logarithm on each side, what I'm going to do is cancel these logarithms. The way to cancel logarithm is using an exponent base. If I look at this logarithm, though, there's no base written here, so I might be questioning, what is that base for this logarithm? But if you recall back a couple of sections, we talked about, again, these 2 special kinds of logarithms where we're going to abbreviate the symbol and not write the bases. One was the common logarithm that we saw in the previous problem. The other is the natural logarithm, which is what we have here. Remember, the base for the natural logarithm is e. So I'm going to use the exponent base e to both sides. Okay. And so I know the exponent base e will cancel the log base e. And what I'm left with is this polynomial equation. So to solve this, I'm just going to FOIL this out. So 3x squared minus 3x minus 2x plus 2 is equal to x squared. And when I combine like terms and move everything onto one side, if I subtract the x squared over, I get 2x squared. I combine the 3x and the 2x to get 5x. And plus 2 is equal to 0. So what I have now is something that's a quadratic equation. I could try to factor this. I think it will factor. But since the leading coefficient of 1, if I do try to factor, it kind of takes, I have to use that long factoring method. So instead, let's just use the quadratic equation, or the quadratic formula, excuse me, because I know that's going to take not very much time. So negative of negative 5 is positive 5. Square root of 25 is, or square root of 5 is, I'm sorry, negative 5 squared is 25. And 25 minus 8 is, oh, jeepers creepers. Hold on, folks. This is 4AC. So 25 minus 16 is 9, and the square root of 9 is just 3. So if I do 5 plus 3, that's 8 over 4, or just 2. If I do 5 minus 3, that's 2 over 4, or 1/2. So those are my two solutions, but I'm not done. I gotta make sure I go back and check this to see if either of these two work. Or give me, if I have to, actually I'm really just checking to see if I get a negative value inside my logarithm. So I have to go all the way back to the very beginning. If I plug 2 in, 3 times 2 is 6 and minus 2 is 4. That's positive. 2 minus 1 is positive. And then if I plug in there, I'm positive. So 2 works. Now let's check the 1/2. So 3 times 1/2 is 1.5, and 1.5 minus 2 is negative. That's already all I need to see. That solution is extraneous. We're going to cancel that and list only one solution. That one solution is 2. So again, got to be a little bit more careful with the logarithmic equation. We got to make sure that we're solving, or after we've solved, that we go back and check to make sure that the answers that we have do not give us a negative value inside of our logarithms. The numbers themselves, it doesn't matter if they're positive or negative. We can have negative answers that work. We can have positive answers that don't work. What we have to worry about is when we plug them back in to the original equation, that we do not get a negative value inside the logarithm. As you see here, we had a positive 1/2, but it did give us a negative value inside of at least one of the logarithms, and all we need is 1. So you notice I stopped checking as soon as I saw one of them being negative. The magic of editing, we have the last piece of this section 15.4. So in the last, we're going to talk about 4 kind of real-world situations in which we have some real-world phenomena that are described using exponential or logarithmic equations, and do some examples of story problems involving those situations. So the first situation is going to be sound intensity. So sound intensity is measured in a unit called decibels, and that sound intensity is described by the formula beta is equal to 10 times the common log of I over I naught, where beta is the sound intensity measured in decimals, or it's just the number of decibels. I is the sound intensity measured in watts per meter squared, and I naught is another sound intensity that represents the threshold of human hearing, so the quietest sound that could be heard. And so if we want a example here, it says given that the sound intensity of busy city traffic is approximately 10 to the negative 5th watts per meter squared, what is the measure of busy city traffic in decibels? Okay. So what we want is beta, that's sound intensity in decibels. We're given a sound intensity measured in this watts per meter squared. And I naught is a constant. It's always this 10 to the negative 12 watts per meter squared. So if we look at our formula, we have everything we need to just fill this in. And so if we go, we can type this into our calculator. This is also something you could do by hand. Perfectly reasonable to do that, but we have a calculator, so why not use it? Do that, we get 70. I'll just shrink that down so we can see that all the time. Okay. So there's that. So basically just had to plug things in. The next situation, it says the Richter scale is designed to register the magnitude of earthquakes. The magnitude of an earthquake, R, can be found using the equation log of A over T plus B, where A is the amplitude in micrometers of the vertical ground motion at the position the earthquake is measured. T is the period of the associated wave in seconds, and B is a constant that accounts for the weakening of the wave with increased distance from the epicenter. The infamous San Francisco earthquake had a Richter scale magnitude R1 of 7.5. How many times more severe was the most severe earthquake ever recorded? The 1960 Chilean earthquake that had a Richter scale magnitude of R2 equal to 9.5. So if we want to compare the severity, what we want to do is compare the amplitudes. So we have one situation. Oops, T is a constant. And we have a second situation. Okay. So what we're going to want to do is we're going to want to compare A1 and A2. And since it asks for how many more times, what we really want is we want the more severe over the less severe. We want this fraction. Okay? So to do that, I'm going to take the stronger one minus the weaker one. Like this. So I know R2 is 9.5 and R1 is 7.5. I'm just going to now distribute the negative sign. So that these plus b and minus b cancel out. And now what I can do is I can use the quotient property for logarithms. So 9.5 minus 7.5 is 2. And what this is going to do is I'm going to have the numerator divided by, or the positive part divided by the negative part. And I know that this fraction, if I want to divide two fractions, it's the same thing as multiplying by their reciprocals. So those t's are going to cancel out. And I'm left then with 2 is equal to log of a2 over a1. So, to get the a2 over a1 by itself, which is our goal, I need to cancel out this logarithm. To cancel a logarithm, I need to use its corresponding exponent base. Since this is just written log, this is the common logarithm, and I know its exponent base here is 10, or its log base is 10. So I'm going to use the exponent base 10 to both sides of this equation. So those are going to cancel. And I'm left with 100, because 10 squared is 100, is equal to a2 over a1. So we can say the Chilean earthquake is 100 times more intense than the San Francisco earthquake. So small changes in the Richter scale imply large changes in earthquake strength. Okay, next situation is pH. Those of you that have taken a chemistry course should be pretty familiar with this concept. So pH is the relative acidity of a water-based solution, and it's measured by the concentration of hydrogen ions in the solution. And we denote that concentration, which we measure in moles per liter, with this bracketed H+. So the formula for pH is it's equal to the negative log of the concentration of hydrogen ions. So our pH scale starts at 0 and goes up to 14, where a pH of 7 is considered to be neutral, and readings from 0 to 7 are considered acidic, with 0 being the most acidic, and readings from 7 to 14 are considered basic, with 14 being the most basic. So let's look at an example. A really sour lemon is found to have a pH of 2.2, and a bottle of bleach is found to have a pH of 10.2. What are the hydrogen ion concentrations of the two items? Okay. So let's do that first. So let's say we do the lemon. So I know its pH is 2.2, and that's going to equal the negative log of H+. So the first thing I'm going to do is move that negative sign over to the other side. And now I'm going to cancel out the logarithm. Again, this is the common logarithm, so the exponent base I'm going to use is 10. So that cancels the log. And if I go to my calculator, 10 to the negative 2.2 is 0.00631 moles per liter is my concentration. If I look at my bleach, this is 10.2 equals negative log of concentration of hydrogen ions. So again, first step, I'm just going to move that negative sign over. And I'm going to use that exponent base of 10. So again, those cancel out. Now go to my calculator and just do 10 to the negative 10.2. That gives me 6.310 times 10 to the negative 11 moles per liter is my concentration of hydrogen ion. So I've got to be careful. You notice the 6.3, but you got to see at the end that's scientific notation. Okay. So it says how many times greater is the hydrogen ion concentration of the bleach than that of the lemon. Okay, so it's an odd way of asking this because which one of them is the more concentrated? Well, it's the lemon, so really we want the lemon on top and the bleach on bottom. So I can take this number divided by this number, and I get this. Which is about, if I counted that up, that's about a 1 with 8 zeros after, or 9 zeros after it. Let's see, 3. Yeah, 9 zeros, so 10 to the 8th. So the lemon is 10 to the 8th times more acidic. You know, 100 million times the concentration. All right. The last situation deals with Newton's law of cooling. So this describes how a hot object will cool to the surrounding temperature. So the T of T is the current temperature of the object after T minutes. T of M is the temperature of the surroundings, whether that's air, water, whatever. T naught is the initial temperature of that heated object. And K is the constant for the given situation. So each object, depending on the material it's made out of, has its own constant of cooling, whether it's like a metal like iron, or like something like water, or like a food, like we're going to talk about hard-boiled egg here in our example. So that K would be given to you in the problem, or you'd be asked to find it or something like that. Let's look at what we're given here. We're told a hard-boiled egg is heated to 96 degrees Celsius and placed in a pot of 16 degrees Celsius water to cool. After 4 minutes, the temperature of the egg is 45 degrees Celsius. how long will it take to cool the egg to a temperature of 20 degrees Celsius? Okay.